Okay, so good morning, everyone. Welcome back. This is the second week of the ELGA. So I welcome those that are arriving for this first week. And I have just a few announcements before we start. So first of all, some people already asked me, we are going to be organizing the buses to go back to Rio on Saturday during this week, and you will all be informed, so you don't have to worry about it. Tomorrow there is going to be some electricity test at 12:30, and so we were asked to finish a bit before. So tomorrow, exceptionally, we are going to start at 9, so that we end at 12:15. So there are some people that left their laundry that had a problem with the laundry. So the laundry is going to come here to deliver the clothes at 12:30. So please contact the other room during the break. Well, also, it's very nice that we are all socializing, but I ask you again that after 10 p.m. you keep the volume down, so some people need to sleep, and so please be kind. And also, yes, one important thing is that we were told that even though the beach to that side is very beautiful and deserted, it is indeed very deserted, but it may not be so safe. So I ask you that if you want to go for a run or for a walk, you go to the right side and not to the left side. And I think this is all the announcements for now. So it's my pleasure now to introduce Cinzia Casagrande, who's give a mini course on Fano varieties and the Lefschetz defect. Thank you, Cinzia.
Is this working? Yeah. Okay. Thank you, and I'm really happy to be here. So our mini course will be about smooth, complex Fano varieties. And we will focus, in the first 3 lectures, we will focus on the case of arbitrary dimension, and then in the last lecture, we will focus on the 4-dimensional case, on Fano fourfolds, okay? And we want to study some properties of Fano varieties that contain a prime divisor that has Picard number smaller than the Picard number of x, okay? So this is our principle. And in the first lecture today, this will just be an introductory lecture, just to set up some notation and the language and the tools that we will use. And then tomorrow, we will study somehow the baby case or classical case, more classical. Classical meaning that it was studied when I was a PhD student. That is the case when x contains a prime divisor with Picard number 1. For instance, this happens when x is obtained by blowing up another smooth variety in a point, and then the exceptional divisor is a projective space. It has Picard number 1, okay? And so we will see somehow which tools we use to study this situation. And then in the third lecture, we will try to generalize this to a more general setting when x only contains a prime divisor with Picard number smaller than the Picard number of x. And then we will need to generalize our tools to study this more general setting. And then in the last lecture, we will focus on Fano fourfolds. And so we will see how we can apply these results to classify Fano fourfolds with large Picard number. And so the main tools that we will use are from birational geometry in the sense of the minimal model program. So what we will do is when we need a result, I will state it in the form that we need it with no proof, okay? And also, somehow a message that I want to transmit is that these tools are very hard and technical to prove, but not so hard to use. So it can be part of your baggage of tools that you can use in your research area. And so it's good to have an idea of how they work. Okay, so then we can start. So we have X, our smooth Fano. And so we want to introduce the vector spaces n1 of X and lower 1 of X, which is the vector space of 1 cycles in X with R coefficients up to numerical equivalence. So a 1 cycle is just a formal combination of irreducible curves, integral curves. With here I'm taking real coefficients, okay, and numerical equivalence. So if I will denote by gamma, capital gamma 1 cycles, and 2 1 cycles are numerically equivalent. So this is the symbol for numerical equivalence. If they have the same intersection with all Cartier divisors. Okay, and then similarly, yes, and I will denote with square brackets the numerical equivalence class of a 1 cycle. And similarly, we have the n upper 1 of X, which is the same, but with divisors. So this is Cartier divisors with real coefficients, again, up to numerical equivalence, which is defined in the same way. So 2 divisors are numerically equivalent if they have the same intersection with every 1 cycle. Okay? So we have these 2 real vector spaces that are dual to each other. Via the intersection pairing. Okay? And their dimension is the Picard number of X. Which is denoted by rho X. Or sometimes also called Picard rank. And so in general, if you consider the first chain class from the Picard group of X to the second integral cohomology group, in general, this always induces an injection of n1 of X into the second real cohomology group, okay? So in particular, the Picard number is always, at most, the second Betti number. But when X is Fano, so this is just for any projective variety, but when X is Fano, in fact, this is an isomorphism. So we are somehow in a simpler situation, and then the Picard number is just equal to the second Betti number. So in particular, it is a topological invariant. Okay? Okay. Then I want to consider the n1 of curves. And inside here, we want to consider NE of x. So this is the cone of effective curves. Which by definition is the convex cone spanned by classes of effective one cycles, where this just means that in our combination of curves, the coefficients are non-negative. This is effective. So this is a convex cone in a finite dimensional real vector space, but in general, it can be not so nice. For instance, when X is any projective variety, for instance, it can be non-closed. But when X is Fano, this cone has an especially nice structure. So I will state a theorem, which is a consequence of the cone theorem. It's a consequence. So it's not the cone theorem in full generality, that since X is Fano, this cone is a rational polyhedral cone. Okay, so it's a very nice cone. In particular, it is closed because polyhedral cones are closed. So this implies that it is closed. So the cone theorem in the smooth case was proved by Mori in '82. And then it was generalized by many people, in particular Kawamata, Kollar, Reed, and Shokurov. And so in general, when X is not Fano, you have a similar statement, but only in the part of N1 of X where the canonical class is negative. But I will not enter into that. So here we have a nice polyhedral cone. Its one-dimensional faces are called extreme arrays. Extremal is a word from convex geometry that basically means being a face. So extreme array means one-dimensional face. And yes, I also want to comment on this fact that it is a rational polyhedral cone. So this means that in every extreme array, we can find the class of an effective one cycle, which is also rational, so with the rational coefficients. And then up to taking a multiple, we can get integral coefficients, so it's just the class of a curve. And, but in fact, the cone theorem says more. So the cone theorem also says that in every extreme array, there exists the class of an irreducible rational curve. So by this, I mean that C is the image of a map from P1 to X. So it may be singular, but the normalization is P1. And also, we have a bound on the intersection, on the anticanonical degree of C, which is the intersection of C with the anticanonical class, this will be at most n plus 1, where n is the dimension of X. So we have a lot of information on the structure of the cone of effective curves. And why is this important? Because the faces, so the cone of effective curves allows you to construct morphisms from X to other varieties, okay? Not any morphism, but what we call contractions. So what is a contraction? Of X is a morphism f from X to Y, which is surjective. It has connected fibers. And Y is normal and projective. Okay. And so a contraction can be birational when the dimension of Y is equal to the dimension of X, or of fiber type when the dimension of Y is smaller than the dimension of X. All right, and then when we have a contraction, we want to associate to it a face of the cone of effective curves. And no. Okay, so for this is just any, so I'm not asking that the difference of the Picard numbers is 1, okay? And all right, and then given F, we define the push forward of 1 cycles. So if C is an irreducible curve, I want to define F star of C, which will be a 1 cycle in Y. And this is 0 if F of C is a point, or it is D times, oof, I'm too strong. F of C, if F of C is a curve. And what is D? D is an integral number. It's the degree of the restriction of F to C. Okay? And then you can define F star of a 1 cycle just by linearity. Okay? It will be a 1 cycle in Y. And there is a very important formula that relates, the projection formula that relates push forward of 1 cycles and pull back of Cartier divisors via intersection. So for every gamma, 1 cycle in X, and for every D, Cartier divisor in Y, you have that D dot the push forward of gamma is equal to the pullback of D dot gamma. And in fact, this number here is here exactly to have the projection formula to hold. And So once we have this, it's easy to see that the push forward respects numerical equivalence. Because, for instance, if gamma is numerically equivalent to 0 in X, and I consider its push forward here, and then its intersection with every divisor will be 0, okay? And so it induces a linear map between n1 of X to n1 of Y. Okay? And it's also easy to see that this linear map is surjective. Because if you take C in Y an irreducible curve, since F is surjective, you can find an irreducible curve in X whose image is C. Okay? And then this means that the class of C will be a multiple of the image of the class of C tilde, so it will be in the image of the push forward. And then the whole cone of effective curves of Y will be in the image of the push forward, and then the whole N1 of Y is equal to the image of the push forward. Okay? And so the dimension of the kernel of the push forward is the difference of the Picard numbers. Okay. Now we want to associate to F, say, a cone. So we define NE of F to be the intersection of the cone of effective curves with the kernel of the push forward. Okay. So this has a nice geometrical interpretation because it's precisely the classes of curves, one cycles, such that gamma is contracted to a point by F, to points by F. Okay? And so this is the intersection of a polyhedral cone with the linear subspaces. So this will be, again, a cone, but a priori it's not clear that it is a face. Okay, so now we want to see that this is actually a face of the cone. To see this, we take an ample Cartier divisor in Y. And we consider its pullback, D. Okay. And then let us intersect D with a curve. So if C in X is an irreducible curve, then D dot C, now we use the projection formula. This will be just H dot the push forward of C. Okay? And then this is 0 if F of C is a point, or positive because H is ample if F of C is a curve. Okay? So we see, first of all, that D is an F. Nef means precisely that the intersection with every curve is non-negative, okay? And also, we see that if we consider, say, D orthogonal in N1 of X, this is a hyperplane. So D defines a linear form on N1 of X, and I'm considering its kernel, okay? This will be a hyperplane, except in the very special case where Y is a point, and then D is numerically trivial, so this is the whole N1 of X, okay? And whenever you have a divisor, and this hyperplane cuts N1 of X into half spaces, one where D is positive and one where D is negative, okay? But since D is Nef, we see that this hyperplane leaves the cone of effective curves all on one side, okay? So we have a picture like this. And so for instance, D orthogonal may be this hyperplane intersecting the cone in this face. Okay? So we see that since D is Nef, the intersection of the hyperplane with the cone of effective curves is a face. But on the other hand, by this description, we see that this is precisely the set of classes contracted to points. So this is another description of a cone that we associated to our contraction, okay? And so in this way, we see that NE of F is a face of NE of X. Okay. And now we want to see that, in fact, this gives a bijection between contractions of X and faces of the cone of effective curves. So I will state now two theorems. So the first one says that F is determined by its contracted curves, so by this cone. So if we have two contractions of X, F from X to Y and G from X to Z, then they have the same cone, NE of F is equal to NE of G. If and only if, basically when I say the two contractions are the same, what I mean is that they differ by an isomorphism of the target, okay? So there exists phi from Y to Z, an isomorphism such that G is the composition okay? Okay, so this is sometimes called the rigidity lemma. And it's not, you can find it in the first chapter of the Bell's book by rational geometry. And so this is the first important statement. So the face associated to F determines F. And then we have the second important statement, which is actually much deeper result, that whenever we have a face of the cone of effective curves, we can always construct a contraction which has that face as associated cone. So the second result, which is a consequence of the contraction theorem. So we have our smooth Fano variety. And say sigma, a phase of NE of x. Then there exists a contraction such that sigma is the phase associated to F. And moreover, we have a second property, which is important. Moreover, the dimension of sigma is exactly the difference of the Picard numbers. So it's equal to the dimension of the kernel of the push forward. Okay, because see, when we defined NE of F as the intersection of this linear subspace with NE of X, it's not clear a priori that it has maximal dimension in this linear subspace. It could be smaller, but no, in fact, it has the maximal possible dimension, and this is important. Yes, so the contraction theorem was proved in the 80s by Kawamata, Shokurov, and Reed. And in general, when X is not Fano, again, you have a similar statement, but only for phases that are contained in the part where the canonical class is negative. So it's slightly more complicated. And this is important because it gives a very useful tool to construct morphisms from X, so to have geometry. Okay, and then usually the contractions that are considered more often are elementary contractions. A contraction is elementary when contraction F from X to Y, when the difference of the Picard numbers is 1, which means that the associated cone is an extreme array. Okay, so somehow these are the simplest possible contractions because they contract as few as possible curves. Okay, less there is only the isomorphism. Okay, and so I said that general contractions, we have two types, birational and of fiber type, while in the elementary case, we have a more specific division in 3 types. So if F is elementary, has 3 possible types. So fiber type stays fiber type, but the birational case is divided in 2 possibilities. So in the birational case, you can consider the exceptional locus, which is the closed subset where F is not an isomorphism. And you have 2 possibilities. Either the exceptional locus is a prime divisor, or the codimension of the exceptional locus is at least 2. So it cannot happen that there are more divisorial components, more than 1, Or it cannot happen that you have one divisorial component and other components of smaller dimension, okay? And these two cases are called divisorial and small. And also, in the divisorial case, you can check, one can see that the exceptional divisor intersected with NE of F is negative. What do I mean by this? This is a notation that I will use a lot. When I write a divisor intersected with a ray, I mean the sign of the intersection with any class, non-zero class in the ray, okay? So this means that the exceptional, in the divisorial case, the exceptional divisor always has negative intersection with contracted curves, okay? Mm-hmm.
So this is the same thing that some people call extremal contraction.
Yes, exactly, extremal. So I would say that the word extremal is used in different ways depending on the context. Usually, I would say most frequently is used for elementary, okay? But some people also include K negative. So it depends on the context. Which in this case, since X is Fano, is automatic, yes. Yes. Okay, are there other questions? The base typically will be singular, yes. So far, I have just taken Cartier divisors on Y, so it's fine. And then you are right, at some point we will have to worry about the singularities of Y, okay? So Y, in general, Y will be singular, almost always, I would say. And the type of singularities will depend on the type of elementary contraction. And for a general contraction, it's even more likely that Y is singular when a contraction is not elementary. Yes?
Sorry, just before you erase this part of the blackboard, you said something about like this equality that's there, that the dimension of the justified U.
Yes.
They might not be equal in some cases or something, and I kind of missed it.
I said that this is non-trivial, so it's part of the Kohn theorem. Okay, because in general, in other contexts, you can construct examples where you have a cone of contracted curves where the dimension is smaller than the difference of the Picard numbers. Okay, not on Fano varieties. No, in the Fano case, you always have equality. Yes, I'm just saying that this is non-trivial. It's not something that easily follows from the definition. It's a statement, part of the contraction theorem, okay? Other questions? Yes? I cannot really hear. Yes, you're right. So what happens is that Y, we will talk about this. When you have a small contraction, Y will not be Q factorial. So there will be Weil divisors that are not Cartier, and also no multiple becomes Cartier. So if you look at the Picard group made with Cartier divisors, or the class group made with Weil divisors, they will have different ranks. So what do not change is the rank of class group, but the Picard group drops, okay? This was a good question. Other questions? No? Okay. So I want now to start to see, maybe let me check, some properties that we will use, okay, in the study of, tomorrow in our problem. So I want to explain some properties of elementary, contractions with fibers of dimension at most 1. So it can happen that you get an elementary contraction, fiber type or birational, where each non-trivial fiber is a curve. And it turns out that these contractions have very nice properties, very good, much better than a general case. Okay, so I want now to explain this. And so we consider F an elementary contraction. And X is smooth projective. And I want to consider two possible settings. Either X is Fano, or slightly more general, I want to consider the possibility that F is K negative, which means that minus Kx is relatively ample. Of course, if X is Fano, minus Kx is ample, so that's it. But this is more general, okay? And I want to stress that this is essential for the properties that I will state, otherwise they are false. And so we assume that every fiber of F has dimension at most 1. And then we have a series of consequences. So first of all, F cannot be small. Okay, this cannot happen. Yes?
What does ample mean?
It's relatively ample. It means that you can embed X in a product like this, such that F comes from the projection. Okay? You can think that X is Fano, it's fine. Okay. Yes, sorry. Not only F comes from the projection, but the divisor comes from O of 1. Okay? So it's similar. It's not correct what I said. Up to taking a multiple, it's similar to ample. Up to taking a multiple, okay? Okay, so F cannot be small. And this was shown by Wisniewski in 91. Yes. And the second property is that Y is smooth. So I just said that Y is almost never smooth, so you should take this as a very good property. We are in a special situation where the target of our contraction is smooth. And then since F cannot be small, it can be either divisorial or small. And so in the two cases, we have, either divisorial or of fiber type. And in the two cases, we have a good description. So if F is divisorial, then F is just the blow-up of a smooth codimension 2 irreducible subvariety in Y. Okay? So in the birational case, it's very simple. We have a smooth variety Y, a smooth codimension 2 subvariety. When we blow up, the divisor, the exceptional divisor, is a P1 bundle over A. So every non-trivial fiber is P1. Okay? So we have our property. And in the last case, where F is of fiber type, it implies that F is what is called a conic bundle. Okay. And exactly, exactly. So you see that in particular, if you have a Fano threefold and you consider an elementary contraction, if it were small, what it means, so there is no such space for dimension, it means that the exceptional locus has dimension 1 and is contracted to points. So we can apply this result, but F cannot be small. So in particular, this says that smooth Fano threefolds do not have small elementary contractions. While starting from dimension 4, Fano fourfolds have small elementary contractions because you can have a surface contracted to a point. All right. Yes, what is a conic bundle? Which means that, so the general fiber is P1. And every fiber is isomorphic to a plane conic. So we have only 3 possible fibers, P1, the 2 lines, and the double line. Okay? Yes. Okay, this the points 2, 3, and 4 were proven by Mori in the 3-dimensional case, and then generalized by Ando to the case of arbitrary dimension in 85. Okay. Okay. So the principle is that this condition gives very good properties of your contraction. Now I want to see some criteria on an extreme array to have that the contraction has this property, because we want to construct, we want to have a method to get these nice contractions, okay? And so let me say we want to consider elementary contractions that are finite on a prime divisor. D. Okay, so I want to start with the first remark. Okay. Again, I want to consider F a k-negative elementary contraction. So again, you can think that X is Fano, and then it's fine. I want to consider the associated extreme array. R will be an E of F. And I want to consider D in X a prime divisor. And we suppose we make two assumptions that D has positive intersection with R. Remember, this means that D has positive intersection with any non-trivial class in R, and that F is finite on D. So I mean, F restricted to D is finite, okay? And then I claim that F can have only fibers of dimension at most 1. And then say every non-trivial fiber F, capital F of F, has dimension 1. Because, indeed. So this is simple. We take an irreducible component, F naught of F. And we want to show that this is a curve, okay? So we take an irreducible curve, C, in F naught. Okay, then since the curve is contained in a fiber, the curve C is contracted to a point by F. So the class of C belongs to the extreme array. So F of C is a point. So the class of C belongs to R. So by this assumption, we know that D has positive intersection with C. In particular, D intersects C. In particular, D intersects F naught. Okay? But then, the curve C cannot be contained in D because the map is finite on D, okay? And so this means that this intersection is non-empty but finite. Okay, because it cannot contain curves. And then if you have an irreducible variety that intersected with a divisor is finite, this must be a curve. All right? And then this means that then you can apply the theorems that I stated before. And then this means that Y is smooth. And we have two possibilities. Okay. So the first is when F is just a blow-up of a codimension 2 subvariety. And then let's call E the exceptional divisor. Then I claim that E is different from this divisor D. This is simple because, of course, the map is not finite on the exceptional divisor, but it is finite on D, okay? And so the image of D is again a prime divisor in Y. And so we have a picture. So here we will have our exceptional divisor, E, is a P1 bundle. And D, it's like this. Because D must intersect every fiber and cannot contain any fiber. So D will intersect E in an horizontal subvariety for the P1 bundle, okay? And then here we have dy, which will contain the center of the blow-up, okay? Since D intersects every fiber, dy contains A. So this is the picture in the blow-up case. And in the second case, F is a conic bundle, and just we can say that D dominates Y. So in this case, we only have this is our X, and this is D. Okay. So this is what we get when we have an elementary contraction of a Fano variety such that, and a prime divisor such that F is finite on D and D has positive intersection with the ray. Okay? And now, okay. I want to give another condition that implies this, okay? Because basically, I would like to have conditions only on the extreme array, not involving F, okay? So let's see remark 2. Before remark 2, I need to set up a notation that will be important for the whole mini course. So notation. Whenever we have a closed subset of X, okay, we can consider the N1 of Z and the N1 of X. So remember, this is one cycle up to numerical equivalence in Z and in X. And since Z lives in X, they have a natural map relating them. Okay? And in fact, this can be seen as, so if this is the inclusion, this is the push forward under the inclusion, but it's just, if you take, you consider one cycle in Z up to numerical equivalence in Z, and you send it to the class of the same cycle, but now up to numerical equivalence in X, okay? And in general, this map does not need to be injective because numerical equivalence can change. For instance, if you consider a quadric surface as P1 cross P1 in P3, okay? And you consider Z as Q, and then this map will not be injective because the two lines of the rulings are not equivalent in the quadric, but they become equivalent in P3. Okay, and we are interested in the image of this subspace in here that I denote by N1 of Zx. This is the image of N1 of Z inside n1 of x. And this can also be defined as so n1 of zx is the linear span in n1 of x of classes of curves in Z. And also we can see it as one cycles in Z up to numerical equivalence in X. Okay? So you can see this map from N1 of Z to its image as a, so here we are already taking the quotient up to numerical equivalence in Z, and then here we are taking a further quotient, possibly, which is up to numerical equivalence in X, okay? And then this, we see that the dimension of this subspace is at most the Picard number of Z. And we will be interested in this, especially when Z is a prime divisor. Okay, so I will come back on this tomorrow. But basically, when I said at the beginning that we want to study Fano varieties that contain a prime divisor whose Picard number is smaller than the Picard number of X, it was slightly imprecise. What we actually want to do is to study Fano varieties that contain a prime divisor such that this space N1 of dx is smaller than the whole N1 of x. Okay? Okay, and now I need this notation to give this second remark. Remark 2. Now we take x, smooth Fano, and let R be an extreme array. No. And we take D, a prime divisor. Okay. And now we take R, an extreme array. Such that, so we keep the first condition that we saw in the first remark. So D has a positive intersection with R. And then I want a second condition that will imply that the associated contraction is finite on D. And the condition is that R is not contained in N1 of dx. Okay? So you see that these conditions involve only the extreme array and not the contraction. Oh. Mm-hmm. Let F be the contraction of R. Mm-hmm. And then I claim that F must be finite on D. Okay. This is again simple to see because if there exists some C in D irreducible curve which is contracted to point, then since the curve is contracted to a point, this means that its class belongs to the extreme array by definition, because R is an E of F. Okay? And but then you see that we have a contradiction because C belongs to R and also to N1 of the X because it is a curve in D. So we said that this is exactly the linear span of classes of curves in D, okay? And then R is a half line. This is a vector space. So this means that R is contained in N1 of the X. And this is not against our assumptions. Okay? So in this setting, we can conclude that F is finite on D, and then F has fibers of dimension at most 1, and then again we have the two possibilities, the blow-up or the conic bundle. All right. So are there questions? It's a good moment. Yes. Yes. Yes, sorry. It means exactly that R is an E of F. So maybe I should have. So by this contraction theorem, I say that for every face of the cone of effective curves, we have a contraction. Okay? So in fact, we have a bijection between the contractions of X. So here X is Fano. And the faces of the cone of effective curves. So here I mean up to isomorphism of the target. Okay? So when I say the contraction associated to a face, I mean that I'm taking the face, I'm applying the contraction theorem, and I get an F such that that face is an E of F. So this, okay? So this is the power of this technique, that we can we have a nice rational polyhedral cone, finite dimensional, and we can use it to get morphisms. Okay? And then you see the principle should be that information on the cone, like in this case, information on the extreme array gives information on the map. Okay? Other questions? Okay. Then maybe we will start to apply these remarks. To the first problem that I mentioned. So we want to study X Fano that contains a prime divisor D with pK number 1. And I say that one example of this is that is when X is a blow-up of another variety at a point, and D is the exceptional divisor, which will be a projective space, so it has pK number 1. Okay? So of course, this always happens when X has pK number 1. So you should think that what we are doing will be meaningful when the pK number of X is bigger than 1. Okay? So we are studying, with these techniques, we are studying Fano varieties with pK number bigger than 1. Okay? In fact, we need a more general, we need a weaker, it's enough to get a weaker assumption. So more generally, with the dimension of n1 of dx equal 1. Okay? So this is the assumption that we make that is weaker than this, because now I have erased, but in general, this dimension is less or equal than the pK number of D. And yes, in the whole work that we will do, we always work with this dimension instead of the pK number of D, because we always work in X. So we always see numerical equivalence in X and never actually in the divisor D. Okay. And now, since D is an effective divisor, it has there exists some curve which has positive intersection with D. Just take a curve which intersects D, but it is not contained. And then this means that there exists some extreme array such that D has positive intersection, because so every curve, the class of every curve can be written as a positive sum of classes in the extreme arrays. So of course, if D had non-negative intersection with every extreme array, then it should have non-negative intersection with the class of every curve. So if we have this, we must have this. Okay. And then we consider the associated contraction. So this is a contraction such that R is NE of F. And then we have two possibilities. Either the ray is contained in this linear subspace, or it is not contained. Okay? And we want to study the two cases separately. So the second case is the case that we studied before. And then the map will be finite on D, and so on. We have nice properties. Okay? And now let's start from this other case. And in this case, I claim that X must have pK number 1. So, say claim if R is contained Okay. Why is this? Let's prove it. So first of all, I claim that we must have that D is contracted to a point. Why is this? Because if C in D is an irreducible curve, okay, then the class of C belongs to the cone of effective curves, and also it belongs to N1 of the X. Okay? But what do we know about this intersection? This has dimension 1, so it's a line. Okay? So the intersection will be, say, 0 or a half line. Okay? And then they both contain R, because R is inside here, and by our assumption, it is also inside here. So the intersection must be exactly the extreme array. Okay? So what are we using? We are using our key assumption that the dimension of N1 of the X is 1, and that the array is contained. So this intersection is the array. So every curve inside here is contracted to a point. So this is dimension 1. Okay? And then, since every curve in the divisor is contracted to a point, this means that the whole divisor is contracted to a point. Okay? And then so in particular, you see that if F is birational, then D is contracted to a point, so D must be the exceptional divisor. But I say that this is impossible. Because of the sign of the intersection with the extreme array. Because we said that the exceptional divisor in an elementary divisorial contraction, so this means in particular that F is divisorial, the exceptional divisor always has negative intersection with the contracted curves, but D has positive intersection with R because we have chosen in that way. Okay, so D cannot be the exceptional divisor, so this means that F is not birational. Okay, so we are left with the case where F is of fiber type. So we want to show that the Picard number of X is 1, and F is elementary. So the difference of the Picard numbers is 1. So we actually want to show that Y is a point. Okay? And so we assume that Y has positive dimension, and we reach a contradiction. Okay, so if Y has positive dimension, let's choose a point in Y which is different from the image of D. And then we take the fiber over Y naught. Okay? So this has a positive dimension because F is of fiber type, and it is disjoint from D. But I say that this is again impossible. This is again impossible, again because of the sign of the intersection with the extreme array, because if we take a curve in F, it's contracted, so its class belongs to the extreme array, and it will have intersection 0 with D. But we have chosen D such that D dot R was positive, okay? So this says that if C in F is a curve, then the class of C belongs to R, and D dot C is 0, but this is impossible. So D cannot be disjoint from a contracted curve. Okay, and so we have also excluded the case where the dimension of Y is positive. So Y is a point, and the Picard number of X is 1. Okay. Okay, so are there questions? Maybe I will just sum up what we have done today in this lecture. We have started from a smooth Fano variety, and we have introduced the cone of effective curves, and we say that it is a nice rational polyhedral cone. And then we say that we have defined a contraction of X, which is a map, which is surjective, connected fibers, and the image must be normal and projective. And we say that can be fiber type or birational. And we have associated to each contraction a face of the cone of effective curves, which contains the curves contracted to points. And we say that this is actually a bijection. So given a face, we can get back a contraction. And then we have seen some nice properties of contractions in a special case, the ones which are elementary with fibers of dimension at most 1. And I say that these cannot be small, and they are very nice because they are just either the blow-up of a smooth variety in a codimension 2 smooth subvariety, or a conic bundle onto a smooth variety. Okay? And then we have seen some criteria to get such a map. And the criterion that we will use is that when X is Fano, when we have an extreme array R, which is not, and we have a prime divisor, D, not contained in N1 of dx, and D has positive intersection with R. Okay, in this case, we have seen that the associated contraction is finite on D, and then it has fibers of dimension at most 1. Okay, and then I have started to study Fano varieties containing a prime divisor D with the dimension of N1 of dx equal 1. Or more generally, or more specifically, if D has Picard number 1, for instance, a projective space. And then we said, let's just choose an extreme array which has positive intersection with D. Then we have two possibilities. The extreme array can be contained in N1 of dx or not. And when it is contained, we have proved that the Picard number of X is 1. Okay? And so we are left with the other case where we can apply our criterion, and we will study this tomorrow. And so I can already tell you that we are going to prove that the Picard number of X under this assumption is at most 3. Okay? So if a Fano variety is obtained from another variety by blowing up a point, The Picard number of x is at most 3, and in fact, this is a very special situation. Okay. So if you have other questions, or okay, otherwise we can stop here.